All right, so this is section 5.2. It's going to be a continuation of what we did with the Riemann sum. Okay, so specifically, if you watched the overview section, or you were here for the overview section, we've already given the fundamental theorem of calculus, which is the big result which greatly simplifies what we're going to do in section 5.2. We can't use the fundamental theorem of calculus to help us with 5.2. Okay? So, in the last section, meaning 5.1, we worked only with positive value functions. So there's going to be some repetition today because I've already done the overview of this. So I now want to define what I mean by net area. So given a function, sometimes that function might be above the x-axis. Let's see here. Sometimes that function might be above the x-axis. Sometimes it might be below the x-axis. And if we were looking at the net area between A and B, we need to talk about how we want to count that. Okay. So the way we'll do that, and this should make sense. In fact, let me not draw the strips like that. Let me actually draw Riemann sums. If I drew some of these rectangles, which is what we'll use for the approximation of the area, certainly each one of these rectangles that I just drew have functional heights that are all what? Positive, and so each one of these gets counted as a positive area. But once we dip below the x-axis and we start drawing some of the rectangles that become our Riemann sums, then just because the functional value is negative, the height is negative, then continuing with this Riemann sum procedure, this region just gets counted as negative. Okay? So it's important to realize, and let's continue on just a little bit further, that these regions get counted as positive versus this region that gets counted as negative. Okay. What else do I want to say? I want to say that from here on out, because we're going to be taking a limit procedure in this section and we'll be done with this, let me just show you. From here on out, when I want to talk about breaking up this interval from A to B into rectangles, I'm going to draw the rectangles just as very fine lines like this. And that's how I'll represent doing a Riemann sum. And that should give you a clue as to what's about to happen. The thickness of those lines that I draw becomes arbitrarily small. Okay? But I still want to keep in mind which way was I creating the rectangles. And so these are my rectangles here. They're very thin now. And let's see, let me take that out real quick. They're very thin now as I'm drawing them, but notice that I'm moving from left to right as I draw those rectangles. Okay. Specifically, what am I not doing? I'm not moving from bottom to top as I draw those rectangles. Okay, I'm not drawing rectangles like this. I'm drawing them like this. Okay, so we'll see that in section 6.2. I've already kind of hinted at that already. Okay. So the net area, so I'm defining net area of a sum of a region R is the sum of the subregions that lie above the x-axis minus the sum of the subareas that lie below the x-axis. That's how we're choosing to define net. Just kind of to give you a general definition of that. Okay. Meaning we basically we have this concept now of negative area, which doesn't fit with, say, if I gave you a carpeting problem and said carpet this region, but it does fit maybe in terms of, say, if the red curve represented your change in profit, then the area is your profit, and sometimes your profit returns positive quantities, sometimes it returns negative quantities. Okay. So we're now in a position to define the definite integral of a continuous function. Okay? So as opposed to in 4.9 where we define the indefinite integral, we're now ready to define the definite integral of a continuous function on a bounded region. Okay? We should interpret the definite integral as the net area of the region R that's formed by that function and the x-axis. Okay. I now want to take some time to talk about this, and unfortunately, I didn't go through and erase these notes, so you had to fill them in. So I'd like to practice writing them because I'm uncomfortable with this notation. You are too, so you should practice writing it. Okay? So the symbol that we're going to use for the definite integral will be from x equals a to x equals b of f of x dx. So this is the notation that we'll use for net area. But that's just notation. What is the definition of this? The definition of this is the limit as delta xi goes to 0 of the Riemann sum. So here's just a generic Riemann sum from I equals 1 to n of f of xi star delta xi. That's just a generic Riemann sum. And what am I doing? I'm taking the limit of the Riemann sum as what? The widths of the rectangles go to 0. We already hinted at this way back in our notes for 5.1. Way back in our notes for 5.1, let's see here, we had this diagram here. And notice what happens as I continue and get better approximations of the area underneath the curve. What happens to the widths of the rectangles? They get smaller and smaller. I'm looking at the limit as the width of those rectangles goes to 0. Okay? So, so here. So this is the definition then of the definite integral. Okay? This is one of my goals for this course, is that you recognize the definite integral as a limit of the Riemann sums. Okay? Because in just a moment, we will only write things this way. And where's the limit symbol in that expression? There isn't one. It's buried in the notation. Okay? Just like when we write the derivative symbol, f prime of x, there's no limit in that. But remember, it had a limit definition. Okay? Same thing. There's no limit when I write this thing out, but I want you to see it as a limit. Okay? Now, the author did a really good job in that he defined this to be for all partitions widths, and for any choice of xi star, any value in this. So this is an extremely, to say that this limit exists is an extremely difficult thing to prove. To show that that limit exists abstractly in the general Riemann sum. It's extremely difficult to prove because each one of these rectangles' widths is going to 0. And who's going to 0 fastest? Well, so there's a lot happening here, as well as it has to hold for any partition that you make. And there are how many different possible partitions that you can make? Oh, yeah, you couldn't count them. Okay? So that's an extremely difficult limit definition, but it is the true definition. So kudos to our author for using the more complicated but correct definition. Okay? But what we'd like to do is go ahead and make this a little bit easier on the eyes. Okay? So first of all, let's say if f is continuous, then this above limit will exist. Okay, so remember we've always had to put provided the limit exists when we gave the limit definitions. We have to put one here. Okay, right here I put it, provided the limit exists. When will the limit exist? As long as f is continuous. That's better than the requirement for f to be differentiable, right? All this has to be is a continuous function, and you can do this procedure, okay, which is really nice. Actually, there are some functions that are discontinuous, and you can still do this procedure. But in our class, we'll say if it's continuous, we can do this procedure, the limit will exist. Okay? So what does this mean? Here so this is the information I'm going to put into 7, but I just want to continue with this. That's kind of confusing for you, so let me write it here. So if all the delta xi's are the same, then we can replace this definition with just delta x. So we'd say the integral from a to b of f of x dx is just the limit as delta x goes to 0 of f of xi, oops, I forgot my sum, of the sum from I equals 1 to n of f of xi star delta x. Notice that this is a much simpler limit, because now there's just one quantity that's going to 0, not all the widths of the rectangles, just the width that's common for all these rectangles is going to 0. But it still has to hold for any partition. But we can actually simplify this one step more. And this is related to this expression here. What did we say? Oops, here I said. Here I say it. What is delta x? It's b minus a over n. So if I solve this for n, we'd have this expression. So as delta x goes to 0, if this quantity right here is going, if this quantity is getting small, what's happening to this fraction? It's becoming arbitrarily large. So that means I can rewrite this one more time as the limit as delta x goes to n. Oops, sorry. Oh, that made no sense. I'm sorry, folks. The limit as n goes to infinity of the sum of the Riemann sum. The sum from I equals 1 to n of f of x I star delta x. So it's this formulation that I want to spend a couple minutes talking about. So we said that the integral from a to b of f of x dx can be defined by this much simpler limit. Okay, so a lot of calc textbooks just give the limit this way. They don't ever talk about partitions. They don't worry about different widths. They just jump straight to here. Okay, which I think is a great starting point as you're getting used to this, but it's good to know that there's a more complicated definition out there. So I want to spend some time explaining this definition to make sure that it makes sense. So I want to talk about our choice of notation here. Okay. Earlier I said, why did we use this symbol sigma? Because it started with the letter S, and so does sum, right? So what is this symbol right here? Well, we call it the integral symbol, but what does it look like? An elongated S. What do you think that S stands for? It's a sum. But where this was a discrete sum, we're adding up countable number of rectangles, this is an infinite sum, which is much more complicated to think about. Okay. Now, what did this whole entity represent right here? It represented the area of the ith rectangle, right? Okay. So what do you think this represents right here? The area of a rectangle. Now, it's not the ith rectangle, because this is uncountably many. Okay? This is far more complicated. Okay? But this is the area of a rectangle. Okay? Now, what was just? Oops, I meant to write that in red. So what was just this quantity right here? Just the f, in terms of the rectangle. This was the height, right? This was the height of a rectangle, so this is still the height of a rectangle. Do you see how everything's lining up, this choice of notation? Okay. And so then what was delta x here? What was delta x? It was the base of the rectangle. Or let's go ahead and just say the word width, just because that's I'll sometimes use that more. Sometimes I'll use width too. Okay. So what is this? What is this differential x? How can you think of it? This isn't quite true, but you can think of it as a width of a rectangle. Okay. So do you need that dx when you write this notation? Oh yeah, or unless you want to be adding up a bunch of rectangles without any widths. Right? So you do need that dx. Okay? So when I look at this definite integral symbol, when I look at this symbol, I see this entire expression. I see that I am adding up a bunch of rectangles whose height is f of x and width is arbitrarily small. Why did it become arbitrarily small? because n went to infinity, the number of rectangles went to infinity, so what happened to the widths of those rectangles? They became arbitrarily small. Okay? And where does A and B show up in the original formulation of this? It shows up by the fact that really delta x is b minus a over n. So everything's there. All the components are there. Okay? So this is a really brilliant choice of notation. Okay? Sometimes math, I mean, you work with complicated ideas, but by making good choices in notation, you can make the complicated ideas easier to understand. All right. So that's our notation for the definite integral. My goal is that you recognize that this is a what? It's a limit of your Riemann sums. The definite integral is simply a limit of your Riemann sums. And the picture from right here is the summary of that expression. If we want to approximate the area underneath the, well, no, if we want to give the true area underneath the curve, by true area I mean net area, if we want to give the net area underneath the curve, we simply take the limit as the number of rectangles goes to infinity. Okay? Now, really, again, really kudos to our author for doing the right notation here. Really, what's happening is the widths of the rectangles are going to 0. That's the real way to think of it. But all of us choose to think of it as the number of rectangles are going to infinity, which is a consequence if they all have the same width. Okay. All right. Or even if they don't have the same width, but we can write it nicely if they do have the same width. Okay. Some more vocabulary. If you can find the net area underneath the curve, then we're going to say that it's integrable on that region. Integrable just means that that limit exists. So what have we already said? We said that limit will always exist as long as the function is continuous, so therefore all continuous functions are integrable. We brought you up to the 1900s as far as math goes. You're pretty good. The real question is which functions that aren't continuous are integrable as well? And that was answered in the 1900s. All right. For number 10 here, I'm going to make you do one more thing for homework. Okay? I haven't posted it yet for your class, so I will post it. I'm going to see the posted notes. So I'll do this during the break, where I have filled this out for you. Okay? And I start with the most abstract Riemann definition, and we simplify it down to the definition that I just gave you. Then I pick the right endpoint method probably to do this, and I evaluate this with the right endpoint method, evaluating not just the first 40 rectangles or the first 100 rectangles. I take the limit as n goes to infinity, and we actually get this value. I do want you to do this one because we're going to get an answer that we danced around in our 5.1 video. So in 5.1 we did look at, this was what we were calculating, this is what you did your Riemann sums on. I think you had to do it 3 different or maybe 4 different times in the notes for 5.1. Okay? And we always got better and better approximations. We're actually going to find the true answer using limits. Okay? And that's what this will go through. So what I want you to do is you just have to copy it over. Okay? So it'll be right below the 5.2 notes. It'll be a little handout. It'll say something like limit with sums or something, or integral with sums, and you'll go ahead and just copy it over. That's all I'm asking you to do is copy it over to see what's going on. Okay? I will not put one of these questions on your exam. Okay?
From like all of 5.2?
No, just one of these where you have to evaluate the Riemann sum with limits. Okay? But I will do one more example of this later on in this section. Okay, but this one is particularly messy, but I like doing it because it was also one that we did the Riemann sum with for approximation methods, and so then we'll get an exact answer using the limit definition of the definite integral. All right, so what I want you to do is for next time, bring this to class on Wednesday, and again I'll just do a quick spot check, see that you copied it over, and you get points for doing so. Okay. Let's look at number 11 here. Number 11 is a backwards thinking question. I am asking you to find the net area underneath the curve f of x equals the square root of 1 minus x squared. I'm asking you to find the net area of that function between x equals 0 and x equals 1. Okay. Well, this is not one that you want to use the limit definition of the Riemann sums on. Okay. I have no idea how you would do that with the limit definition of the Riemann sums. It is an absolute mess. So maybe you think, well, maybe I should try the fundamental theorem of calculus since he's already shown that to me. You can try, but you won't be able to find an well, I shouldn't say that. You will most likely be unable to find an antiderivative to this function. Okay, you need tools that you'll learn in Calc 2 to find an antiderivative of this function. So what can we do? Well, let's remind ourselves that we're computing what? So this is going to come out to be a number that represents what? The area underneath the curve. Well, let's look at this curve. What does this curve look like? No. Absolutely not. In fact, kind of the opposite of a straight line. Jigme, what were you showing earlier? It's a circle, right? If I have a circle with radius 1, what's the equation of that circle? It's 1 equals x squared plus y squared. If I solve that for y, what do I get? I would get that y is equal to plus or minus the square root of 1 minus x squared. So that would be the equation of the circle, right? Given as two different, I'm not going to worry about writing it as y1 and y2. Those would be the two equations that give you the description of the circle. We only want the one that returns positive y values. So what is the graph of this? It's not a circle actually, but what? Semicircle, and it's specifically the upper semicircle. So we recognize, oh, this is the graph of f. Okay, it's a circle with a radius of 1. Or a semicircle with a radius of 1 centered at the origin, the upper semicircle. And what am I asking you to do? I'm asking you to compute this area right here. So this is why I'm saying this is a backwards question, and you get these a lot in section 5.2 because we don't have a lot of means for computing areas. And so one thing you'll have you do is just use geometric properties to compute areas. Okay. So what is this quantity? So Sarah was exactly right when she said you should get a number at the end of this. I completely agree. And the number should represent the area of that shaded region. But what is it?
Pi over 4.
Yeah. This is a circle of radius 1, so what's the area of the entire circle? It's pi r squared, so it would be pi times 1 squared. So the area of the entire circle would be pi, and we're looking at a quarter of it. So the answer to this is pi over 4. So this is an atypical question. Let me just label this as a backwards question. Rather than using calculus to find area, we're using areas to do calculus, which is kind of silly, but you'll have a lot of conceptual questions based on how you know how to compute areas of things already. Okay? So for example, if I give you a function that looks like this, how would you find the area underneath this curve from A to B? You would just find the area of this little triangle and then maybe find the area of this rectangle, and you would add them together. Okay, so that has nothing to do with using limits of Riemann sums. It has nothing to do with using the fundamental theorem of calculus. It's just, hey, I already know how to compute areas, and you're welcome to, or that's how you're expected to do them in section 5.2. Okay? Again, once we get to 5.3, we've got better tools, and so these backwards questions don't show up as often in those. Sage.
Why did you say this was a backwards question?
Yeah, it's a backwards question because what do we use the definite integral for? To compute area.
Curve. Yeah.
Area underneath the curve. But what did we do? We used our knowledge of the area underneath the curve that we already had to answer this calculus question. Right? So we don't have the tools to answer this with calculus, but we do already know everything about circles from,
Geometry.
yeah, whenever we learn
I
circles.
forgot geometry, honestly.
That's all right, that's all right.
I took it in high school.
Are there gonna be test questions like this?
Probably not, because I'm more interested in using calculus. Now, I do find ways to make sure that you understand, to make sure that you understand that this expression right here represents an area underneath the curve. But because we're learning all these calculus tools, I probably wouldn't give you something that you couldn't use a calculus tool on and frame it as a calculus question. Okay? If I were to do this, I'd say, find this area using geometry, or give you some sort of hint to not use calculus to do this. Yeah, I can't promise I won't ask a conceptual area question, but I would give you, if I wrote out a calculus expression, I would tell you to use some other skill if you can't find an antiderivative of that. Okay, so I now want to spend some time going through some properties of the definite integral. We've already looked at these properties when we gave the fundamental theorem of calculus in our overview. So you've already seen most of these properties. But actually, proving these properties is far simpler once you think of this expression as a Riemann sum. And let me just show you. So in the Riemann sum of this expression, we would have the limit as n goes to infinity of the sum from I equals 1 to n of f of xi star plus g of xi star all times delta x. Come on, give me a break. All times delta x. Okay. But what could I do with this delta x? Based on just the basic real number properties, delta x is a number that stands for a width. And I could distribute it over a sum by my distributive property. Okay. And then what can I do? Well, if you wanted to add up a bunch of sums of binomials, you could just add up all the left terms and then all the right terms and then combine them together. So it just falls back on the fact that we already know how to use the associative and commutative and distributive properties inside the limit. So before we take the limit, we break it all up into a bunch of pieces, and then we can distribute the limit over the sum. And so that says, hey, if you want to find the area underneath the curve of the sum of two functions, you could find the area underneath the curve of the first function and add to it the area underneath the curve of the second function. All right. The next one is again kind of the same idea. This right here would be the limit as n goes to infinity of the sum from I equals 1 to n of c times f of xi star delta x. But c doesn't have a counter variable with it, right? So it's a constant, so I could first factor it out of the sum, because constants, basically it's factoring, it's doing the distributive property backwards. So I could pull the c out of the sum, and then I could, one more time, since limits of since constants factor out of limits, I could factor it all the way out of the limit, and so it's just c times that area. Okay? All right, so we'll talk about the rest of these. Actually, they're all kind of important. From here on out, when you see an expression like this, what shape do I want you to think of? Yeah, when you see a product of two quantities, that is a rectangle. In some way, there's a way to think about the problem as a rectangle. Okay. Specifically, if this is my curve y equals c, and I'm asking you to find the area between A and B, what is the area of this region? It's just the area of that rectangle. How do you find the area of a rectangle? You would take its height, which is c, and multiply it by its width. Well, what's its width? B minus A. So from here on out, when you see an expression like this in this chapter, I want you to think of it as just the the area of a rectangle. It is a height times a base. Oh, it's all right.
I didn't get that either, actually. No, I'm just kidding.
Okay. Should ask Siri some indeterminate form questions. She's pretty good at them.
All she does is look them up on Google, so she doesn't actually.
No. Ask her what 0 divided by 0 is.
What does she say?
Doesn't she like explain cookies or something like that?
Yeah,
You
it's
have
okay.
0 friends or something.
Yeah. Yeah.
Rescue.
Alright.
Or if you ask Siri, if you tell her like, "Hey, I'm drunk," like she'll be like, "Hey, do you want me to call you an Uber?"
Oh, really?
Yeah. So
Have you ever
she's
tried
pretty.
that?
I like the different questions you and I have asked Siri.
Try the fire truck one.
All right, let's keep going. Does this one make sense? This one should make intuitive sense, I think. That if we're looking for the area beneath the curve of just a point, that area, that pointwise area is 0.
This is a constant.
What, of course, is interesting is when we do the integral from a to b of f of x dx, at each point we're taking and plugging in an x value, multiplying it by an arbitrarily small width. So any one of those is 0, or approaches 0, but the sum of a bunch of things approaching 0 comes out to be the area underneath the curve. That is the indeterminate form in this problem. All right. This just says what? Take a moment to read this. I guess I didn't say this. H of x is less than 0, so what should be the net area? A negative number. That's all that's saying. All right? If your function is below the x-axis on the interval, then when you compute the definite area, it should come out to be a negative number. Okay. We already looked at this one, okay, where we said, hey, if we interchanged a and b here, you can do so, but you just put a negative sign in front of it. And that's related to the fact where, what was delta x? Delta x is b minus a over n, right? So if normally when we write this, let's just think of it as what we normally write it, a is less than b. So that's why delta x was always a small, but what quantity? Positive. And if I interchange those, then all my delta x's would be small and negative. So every single, in the Riemann sum, every single term would be f of xi star times delta x, where that each one of those is a negative quantity, right? And so I could factor the negative out of all of those, and then factor it one more step out of the limit, and that's where that negative sign shows up. So by interchanging the limits, I'll change the sign on delta x, and by changing the sign on delta x, I introduce a value that I could factor out of all of them. Okay? All right. Oh.
Is differential x, like in the integral thing, like is that basically just delta x? Like
So at a very kind of so without going too far into the, so you could basically think of this delta x in the Riemann sum. When we look at the limit as n goes to infinity, I equals 1 to n, the delta x in the Riemann sum becomes the differential x in the infinite sum. That's actually related to what theorem?
Mean value theorem.
Exactly.
Really?
Yes.
Holy shit.
Oh wait, it's like that thing you said.
I didn't even know. I
Someone
just
asked
guessed
me
that.
Yeah.
No, you
Just say it.
It's right. It's right. It is the mean
That's
value.
right.
That's where that differential shows up when you use the mean value theorem in evaluating this limit.
I pulled that out of my butt. So.
I know.
You're serious though? It's right.
It's right. It is.
I was about to say
gosh.
mean value theorem too. I had like the n.
Sorry, man. You get partial credit.
All right. Let's keep going, folks. So this one just says, and this is kind of the opposite of one of the earlier ones that we had. If the function's always above the x-axis, then we would expect the net area to be positive. Okay, nothing really exciting there. This one should make intuitive sense. If one function's always above the other function, then the net area of the first should be greater than or equal to the net area of the second. Even if both of them are negative, this will just have a smaller negative quantity than this one, making it greater. All right, this last one I want to spend a little bit of time on because this one will be important in our proof of the fundamental theorem, which we may or may not get to. So this one's saying, let's suppose we've got a function, f of x, between a and b here. Okay. This is, well, what do I think of, see here, this stands for the what? First of all, what does that stand for? What I just underlined, what is this, what does that represent?
Definite interval.
The definite integral, which in terms of the picture is
Area under the curve.
the net area underneath the curve, so that's this number, whatever this number comes out to be, it's that number right there. Right? So what is this saying? It's saying that the net area is trapped between two what types of objects? What did I say to think of these things as? These are two rectangles. So you could trap the area between two rectangles. Where, what is little m? It's a value that's smaller than all of the values in the function. For example, maybe this is little m right here, and this would be this area. So certainly you agree, if m is below all values in the function, then the area of this blue rectangle has to be smaller than the area of that red region. Similarly, oops, let's do, I guess, black. Similarly, if capital M is up here and capital M is bigger than f of x for all values on that region, then this area, my picture's getting pretty cluttered, is what? Larger than the area underneath the red curve. That gives us a really handy way of trapping the area of red between two rectangles. Okay? Specifically, and this gives you a hint into the fundamental theorem, okay? Specifically, if capital M represents the absolute max on an interval, and little m represents the absolute min on an interval, then I can trap some complicated curve between two rectangles. And as my width goes to 0, then these two rectangles, the max and min, approach one another. So that's how we'll use it when we get to the fundamental theorem.
Is it like squeeze theorem?
Yes. Yep. Kind of. The answer to the area question then, and by the way, there's nothing wrong with me saying this, but let me just emphasize this as total area. And for you guys, if ever I ask you for an area question on an exam, I will write either total area or net area, so you don't have to spend time deciding, is he talking about total area or net area? Okay? Now, if I just give you a definite integral, what am I asking you to find? Which one?
Total area.
No. Net area. Okay? And if I give you a definite integral where I take the absolute value of the function inside of there, then I'm looking for the total area underneath that curve. Okay? So if I give you an integral question, it's implied from the way I formulated the question. But if I'm asking a word question, I'll either say total or net. Okay? So specifically here, I'm not talking about the net area. Okay? So how would we find it? The total area is the integral from a to b of the absolute value of f of x dx. How we doing, folks?
And the net is just without absolute value?
Mm-hmm.
Sweet.
That should make sense. Go back to our original picture in this section. So in our original picture, what does the net area do? It counts the regions above the x-axis as positive and the regions below the x-axis as negative. So it gives me net area. But if I take the absolute value of this function, what do? I take all regions below the x-axis and reflect them up, and so it's going to give me total area because all regions will be counted as positive.
That's kind of like speed with.
Yes. Oh, it's exactly like speed.
Okay.
Yes,
gotcha.
it is
So
exactly like speed.
If we were to draw a graph on an exam, we would just mirror the negative areas.
Yes, yeah.
Okay.
In fact, we'll look at that when we get back from the break. Okay, where were we? We're running through properties when we're doing this problem here. Is this Celeste? Oh no. Okay, great. Okay, so we're looking at our properties here. So here, let's find, and here again, when I ask this on a test, I will say total, because I don't want you to be confused. Okay, because it's a word problem, and so I'll use the word total. Okay. Now, if I just gave you a calculus question, you should know whether I'm talking about net area or total area. Okay. All right, so the total area is equal to the integral from 1 to 6 of total area. So what do I need? Absolute value of 2x minus 7 dx. Okay. But I have a hard enough time doing these Riemann sums as is. I certainly don't want to worry about there being an absolute value in the function that I'm working with. So how do we work with absolute values in calculus? We always go back to the definition of the absolute value, which says what? If the expression's positive, leave it alone. If the expression's negative, change the sign on it. Okay? So we need to determine when is this expression positive and when is this expression negative, right? So let's take a look. Here's the graph of this function, okay? And we're looking at it from 1 to 6, right? And we want to compute this total area now, not net area, but total area, right there. Okay? So what do we need to decide? Well, I'd like to go ahead and say, whoa, if this expression's positive, leave the sign alone. If this expression's negative, change the sign. But what's the problem? For the interval we're working over, what? It's both. Sometimes it's negative, sometimes it's positive. So what do we need to do? We need to break this problem up into two separate questions. Okay? So we need to determine, where is this point of intersection? Wrong color. Where is this point of intersection? Well, this point of intersection is 7/2, comma 0, right? So this is equal to the integral from 1 to 7/2 of the absolute value of 2x minus 7 dx plus the integral from 7/2 to 6 of the absolute value of 2x minus 7 dx. Folks, in this section, I'm showing a little bit more work than I would normally show. So once I get to the point where I normally just jump to, I'll show you what I would do. Okay. But for this first region here, let's do this in green. For this first region here, that's this bright from 1 to 7/2. The function's always negative. So how do I take the absolute value? I just change the sign on it. Oops, that's 2. And then for this region, right here, how do I take the absolute value of that part of the function? Don't touch it, leave it alone. So this will be 7/2 to 6, leave it alone, 2x minus 7 dx. Well, what can I do with that negative sign if I wanted to? And I don't know necessarily it's the best idea, but I'm going to do it anyway. What can I do with that negative sign in that first integral? Factor it out. So I'm going to write that as negative integral from 1 to 7/2 of 2x minus 7 dx plus the integral from 7/2 to 6 of 2x minus 7 dx. Okay? And it's this that I would normally jump to. I would write the problem this way, and then I would just jump to here once I had drawn that picture for myself. Does that make sense? So all I would do is break it up, and for whichever regions it was below the x-axis, I would just make sure that I tack that negative sign on those. That should make sense. In fact, I've seen some books kind of backwards, they're kind of not being very careful. They just say, hey, evaluate each one of those. Some of them will come out to be negative. If it comes out to be negative, what do? Change it to be positive. Okay? Questions on that, folks? Okay. Now, this is from section 5.2. I'd like to evaluate this question. This is from section 5.2. I don't have the fundamental theorem. How am I going to find these areas? Yeah, these shapes are just triangles in this case, right? So this first one's going to be minus, how do I find the area of a triangle? I take 1/2, the base of the triangle, which is what? 7/2 minus 1, that's the base, times the what? Times the height. What's the height of this triangle? Well, when x is 1, we're at, I think, -5. How did I get that -5? That's this point right here. That would be this point right here. That's the order pair 1, -5. And so what's the height of this triangle? It's -5. And it's because its height was negative, you see precisely why we ended up putting a minus sign in the very front of it, right? Give me some feedback, folks. How are we doing? Yeah?
I'm just confused as to what you wrote under the 7/2.
Oh, that's the base.
Oh, okay.
Yeah, in fact, let me finish that out. So I wrote that as base, and this is the what? The height. Oops. Height, or, yeah, depth is probably a better word for that. Okay, and this is all in describing the area of this triangle right. This is all in describing the area of that triangle right there. Please.
How did you turn the a equals 1 and then b equals 7/2 to negative with the blue arrow leading to it? From,
So what I'm saying is, rather than showing all of this work in these two lines here,
yeah.
rather than showing all that work, I just say, okay, let's look. So I did look at the graph, and I said, oh, I'm going to break it up from 1 to 7/2.
Oh, you factor out the -1.
Well, that's how I went from here to here. Yes, from this
Okay.
line to this line.
I got it.
But one way to say it is this region right here, from 1 to 7/2, that's always going to be negative, and so I just tack a negative in front of the integral, and that makes it a positive quantity.
Gotcha.
So the net area is negative, certainly, for that interval, but I want total area, so I want to count that negative area as positive, so I change the sign on it. If I lost you on that, just show all these steps.
Well, that's kind of like with limits, like breaking the absolute value sign, right?
Yes.
Like you can just, if it's negative, just pop a negative in front of it.
Yeah, so I used to wonder why every calculus question always asked the absolute value question when it first introduced limits. It's because we basically do that procedure over and over again in this course. Now, we go to the definition of absolute value over and over again. Okay, and then for the second one, we've got this triangle right here. Okay. Well, the base of this triangle, the base of the second triangle will be, oh, sorry, still have 1/2, and the base will be 6 minus 7/2, and then its height would be, well, what happens when we plug a 6 into the function? We get the ordered pair 6, 12, 6, 5. So the height of this second triangle is also 5, coincidentally. That is coincidental. Okay. There's no symmetry there, I don't think. Yeah, because these two widths are different. Okay, and then we can crunch that. Okay, so I'll leave it there. I'm not interested in crunching it. Questions, folks? Actually, I am interested. Let's go ahead and finish this out. Did anyone plug it into a calculator yet? Go ahead and crunch that expression. I'll let you guys do it. What's that?
Is it 0?
bases are different, and
Oh.
this quantity will be positive. That's why we're finding total area, not net area.
12.5.
12 and a half?
I don't know if that's right.
Is that what we get, folks? I need a second. Got a second on it? All right, let's operate on it. All right.
Oh,
No.
yeah, I forgot to flip the signs, because it's 25 fourths plus 25 fourths. And I subtracted them.
Is the net area 0?
The net area would, I guess the net area is 0. If these, I don't know, if this number is the same as this number, which I guess it is,
Yeah, it's.
I didn't think it was, but okay, then I guess it isn't coincidental that those two heights were the same. There's a symmetry there. It would be 0 if we calculated the net area,
I forgot.
but the total area is the sum of those two regions. In this case, they're identical, but there's nothing that says they have to be identical in this procedure. Okay, so I decided I wanted to do this problem, folks, because you guys have already seen the fundamental theorem of calculus. So let's go ahead and utilize that instead. Okay, so let's return to this formulation of the question, minus the integral from 1 to 7/2 of 2x minus 7 dx plus the integral from 7/2 to 6 of 2x minus 7 dx. And let's just check our answer with the fundamental theorem. So this would be equal to x squared minus 7x evaluated from x equals 1 to x equals 7/2 plus x squared minus 7x evaluated from x equals 1 to x equals 7/2. Anyone have any questions about what I just did? Oh, yeah, I'm sorry, this should be, good, I'm glad there are questions. This should be 7/2 to 6. Okay? Any questions on that? Okay, because folks, this is the fundamental theorem. I spilled my guts with it on Thursday. We saw everything to do with it. Hopefully you've been practicing it. Okay? But Thursday was your first time seeing it, and this is the first class period since then. So are there any questions about what I just did? I took an antiderivative of this function here, which would be x squared minus 7x, and then I'm reminding myself to evaluate it at the upper and lower endpoints. Kasha?
You guys specify which way you want us to
Oh no, not for a problem like this.
So we can't answer either way.
Either way. Now, in the My Math Lab for section 5.2, they're assuming you don't know the fundamental theorem. Okay? And so you're using geometric shapes to answer questions, and that's how you should do it. Okay? I would check answers with the fundamental theorem, but on a test, that's like if you said, unless I specify use the limit definition of the derivative to find the derivative, you use derivative rules. Same idea here. Unless I specify, use geometry to find the area beneath the curve, or use Riemann sums to find the area beneath the curve, you're probably just going to use the fundamental theorem in calculus. All right. Folks, these are kind of pet peeve problems for me. I think it's extremely important that you're able to translate problems from limits of Riemann sums to their corresponding definite integrals. I can tell whether you've worked all of the practice test questions, because these aren't hard. And I can also tell who didn't come to class, because this expression, if you have not studied it, looks outrageous, right? That is an outrageous looking expression. What is it? This is the width of a rectangle. This is the height of a rectangle. I'm adding up a bunch of them, and then I'm taking the limit as their widths go to 0. This is just the definition of the limit definition of the definite integral. So how would you write this as a definite integral? You would just write the integral from 0 to 2 of x squared plus 1 dx. That's all I'm asking you to do here. Now, I might also, in subsequent, after we learn the fundamental theorem, I might say, now evaluate this, right? And you would be able to evaluate that as well. But I'm asking you to recognize the limit definition of a Riemann sum and convert it to the definite integral. Okay? In this one, I did this with the most general definition of the Riemann sum, where we had each, I guess I'm saying i's, these are all k's, it's just a different counter variable. Each one of these widths is different. And so we're taking the limit as all of those widths go to 0. That was just from the most general way we could give the definite integral definition. Down here, same idea, but in this case, all of the widths are the same. That doesn't change the definition. I'm still asking you for the definite integral. So this is still the integral from 1 to 2, in this case of x, natural log of x, dx. So all I'm asking you to do is set this up. By the way, this one you probably couldn't evaluate. You don't have the tools to evaluate this one. Basically, you guys know derivatives so well that I could give you any function and ask you to take the derivative of it. And you should be able to do it, no matter how messy it is. I have to be very careful which functions I give you when I ask you to find an antiderivative of it. Just like you guys can expand any factored polynomial, but factoring any expanded polynomial, that's a lot of work. Same idea. Okay, so again, what am I asking you to do? I'm asking you simply to recognize that that is the limit definition of the Riemann, or that is the limit definition of the definite integral. In this case, I'm using kind of the more common version of that limit definition, where the number of rectangles is going to infinity. But it's still the same question. What is the answer? The answer is the integral from 1 to 2 of 4x minus the tangent of x dx.
Is the x star k always going to be x?
Mm-hmm. Yeah. Yeah. So do you see these problems aren't hard? They're not hard, but you have to work them. You've got to have looked at them before, because this notation can just be intimidating at first glance. And it is intimidating to work with. Okay, let's take a break. Let's start up here at 42, please. All right, folks. I now want to actually compute a definite integral using a Riemann sum. Okay? To do this, we're going to need this fact. Okay? This fact is that the sum of the first I cubes from I equals 1 to n, the sum of the first n cubes can be given by this formula right here. It's n times n plus 1 all over 2 quantity squared. Okay? So you'll see, if you remember in the 5.1 video, we gave a couple of formulas that quickly evaluate sums. Rather than having to write them out, there might be a way to evaluate the sum without having to plug in each piece, each term in the sum. And the same thing is true for the I cubed one. Okay? In the notes here for how we do this with x squared plus 3, again, you use a couple of sum formulas. Let me just show you. You use this sum formula and this sum formula, but it's this second one, this squared one, that's a mess, which is why I don't like using it. Okay, that squared one is a mess. Okay? But anyway, those are those sum formulas. Let's go ahead and actually evaluate this definite integral using the limit definition of the Riemann sums. Okay, so here we go. We would say that the integral from 0 to 1 of x cubed dx, and I'm going to go ahead and just go straight to the more intuitive Riemann sum limit definition. That is the limit as n goes to infinity of f of, oops, thank you, the sum from I equals 1 to n of f of x I star delta x. Okay? So here I'm saying that the function that we're working with is the x cubed function. Okay? So that's just, all I've done here is given the limit definition of the definite integral. Okay? And I do expect you to recognize that. That is the limit definition for what this expression is.
Shouldn't it be cubed?
Well, so here I'm only given the function. In a moment I'm going to plug in what this function is. Okay? But before I do that, I want to go ahead and let's pick given it was stated in the problem, let's pick the right endpoint method. So if we pick the right endpoint method, what do we use as our xi star? We're going to use a plus I delta x. That's what we're going to use, and that was I put that up at the beginning of class for the 5.1 notes. So we're going to use this a plus I delta x. Okay? So that means, oh, and let's go ahead and calculate what delta x is. Delta x is b minus a over n. So in this problem, it would be 1 minus 0 over n, which is just 1 over n. Notice the number of rectangles, this is what's different. The number of rectangles is not specified. That's really the only thing that's different in 5.2. And then we take the limit as the number of rectangles goes to infinity. Okay, so now we can rewrite this as the limit as n goes to infinity of the sum from I equals 1 to n of a plus I delta x. Let me go ahead and write it this way once, and then we'll make a comment. So we say f of a plus I delta x times delta x. So all I did here was pick the right endpoint method. Okay. But who's playing the role of a in this problem? Okay. There are only a few of these that I would really ever ask, and I don't ask for you to do this on a test, but there's only a few of these that you really ever want to do by hand. It is a real pain when this a is something other than 0, because now you'd have to cube that binomial, which makes a huge mess, which is sort of what happens in that one that I've asked you to copy over. Okay? But anyway, because a is 0, then we get the sum from I equals 1 to n of just I delta x cubed, because f is the x cubed function, times delta x. Which is the limit as n goes to infinity of the sum from I equals 1 to n. So what is delta x? It's 1 over n, right? So this would be I cubed times 1 over n cubed times that other delta x, which is 1 over n. Okay, I've gone really fast. This is where I'd like to kind of slow down and say, what are your questions? I guess I can go up one more line too if there's questions.
If you're multiplying by 1 over n and n's approaching infinity, you're going to think that one through then, right?
Eventually.
Eventually.
But there are other n's at play here, and we're going to see that. Because this sum also depends on n. So I can't make some statement like, oh, that's going to 0, that's going to 0, so everything's going to 0, because this depends on n, and it's not going to 0. So that's the issue. Yeah. So that's where where calculus gets kind of heavy, in that stuff is kind of buried in there. I once had a class where basically the gist of the class was, when can you pass a limit through an integral symbol? That was basically the point of the class. And the answer is, very carefully in some circumstances. Okay. So be careful with some of that stuff. This sum has an n built into it, so I can't just argue that I've just got two things that involve n and they're both going to 0. Okay. All right, any questions? Okay. So, as we've said once before, this is 1 over n to the 4th power, right? Everyone okay with that? This whole thing is 1 over n to the 4th power. And it does not depend on my counter variable. So what can I do with it? I can factor it out of the sum. Can I factor it all the way out of the limit? No, because my limiting variable is n. So I can write this as 1 over n to the 4th times the sum from I equals 1 to n of I cubed. And basically the secret of being successful with these infinite Riemann sums is breaking them down to these little formulas that we already have rules for. We're kind of passing the buck because we didn't prove those little rules. So we get the limit as n goes to infinity of 1 over n to the fourth. And then what did I say at the very beginning this evaluates to? The sum of the first n cubes evaluates to be n times n plus 1 all over 2 squared. So we clean that up. We get the limit as n goes to infinity. Trust me that if I FOIL it out, we end up with n to the fourth. Oops, let's go ahead and put the 1 over n to the fourth here. If I FOIL that out, I get n to the fourth plus 2n cubed plus n squared all over 4. So let's see what we can do here. I'm going to go ahead and notice I've got this divided by 4. That's a factor. I'm going to take that out as 1/4 the limit as n goes to infinity of n to the fourth plus 2n squared plus n squared all over n to the fourth. Well, we're getting close. We get 1/4 the limit as n goes to infinity. Now let's divide n to the fourth into each one of those terms. 1 plus 2 over n squared plus, oops, I dropped a, this should be a cubed here. So that would make this over n. Plus 1 over n squared. And so what do we get? We get 1/4 times 1 plus 0 plus 0, and we get, what is the limit of the Riemann sum? 1/4. Do. Nobody, even us math nerds, would like calculus if this is how you did it every time. Okay? Nobody would like it if this is how you did it. Okay? As a reminder, somewhere up here, we had the question. Okay, what were we doing? As a reminder, we were computing the area underneath the curve, x cubed, between x equals 0 and x equals 1. And what did we find this area to be? We found the area to be 1/4. Okay. This method, and at some point, I think it's on the on your notes right here. This is me being a smart aleck, I guess. This method of using these sums is tedious, or put whatever. I put tedious, but you could put whatever you want there, wherever you feel about it. You don't really have to fill that in. You could put tedious, you could put awful, you could put, I'm not going to check it, whatever you want. Say how you really feel. Okay. Of course, we've now learned the fundamental theorem of calculus, so let's go ahead and show that. Okay. Here's how we would really do this problem. The integral from 0 to 1 of x cubed dx is equal to what? What do? We take an antiderivative, and we get 1/4 x to the fourth evaluated between 0 and 1. So we get 1/4 times 1 to the fourth minus 0 to the fourth, which is 1/4 times 1 minus 0, which is just 1/4. Far easier to use the fundamental theorem of calculus. Okay? So I will not put one of these questions from where you have to use these sum formulas. I will not put one of these questions on your exam. Okay? You guys are probably the last class that I won't do it for. This class they're going to have to do it.
Thank God for small miracles.
Wait, can you repeat what this said?
The
Yeah, I'm not gonna make you do the longhand procedure of limits of Riemann sum. Now, I have other ways of knowing whether you understand that the definite integral is a limit of a Riemann sum. Okay? So I'm not saying no 5.2 questions will show up there, or conceptually you won't have questions that are along this line, but to me, this is a very tedious method. I mean, I think you learn something by doing the limit definition of the derivative. I'm not sure what you learn by doing the limit definition of the Riemann sum when it takes so long to do these problems. I feel like you quickly lose sight of what on earth you're doing. Okay? But I'm asking you to copy over some of the work, so you get to copy it over. For those of you interested, that is the work that goes with this. Okay? All right. So we'll skip that one. Is that the end? Hooray. Okay.